Hello everybody and welcome to section 1.1. So in this section we are going to be talking about how we measure velocity, a very specific type of a rate of change. We are looking at page 9 in the workbook, and I think the best way to start this discussion is just with a specific example. So let's read this example together. So if an object is fired into the air with an upward velocity of 100 meters per second, its height in feet after t seconds is given by the function f of t equals 100t minus 16t squared, and we're given a graph of that function. Okay, and before we go farther here, let's maybe think about the units that we're talking about here. So on one axis we've got time. They're telling us that's measured in seconds. And height is being measured in feet, just to keep track of that. Okay, and part A would like us to calculate some average velocities. Okay, this is the same idea as what we talked about in section 1.0. We're talking about average rates of change of our function. Okay, so for example, in part 1 here, to find the average velocity between 1 and 4, I'm going to introduce a new notation for that. Our book likes to write that as AV. That stands for average velocity between 1 and 4. Okay, and to find average velocity, we're just really trying to figure out how much change in height do we get and how much time goes by. So we're measuring the change in height over the change in time. And we can do that using our function. The change in height is just going to be f of 4 minus f of 1, okay, the difference between those two output values, over the amount of time that goes by, which should be 4 minus 1. Okay, how do we actually do those calculations? Okay, well, here's where we need our function. So f of 4, for example, that's taking our number 4, and that's a t value, and so we're going to substitute that t into our function everywhere that we see a t. So if we write all of that out, we would get 100 times 4 minus 16 times 4 squared. All of that is f of 4. Okay, and f of 1, same idea. We're just going to take 1 and plug it in for all of our t's. Okay, and then on the bottom we've got a 4 minus 1, which is a 3. Okay, and you can go to your calculator and figure out what that number is. That turns out to be 144. And then this number over here, if you do that arithmetic, that you might be able to do in your head. You're going to get 84. Okay, so putting it all together, we're going to get 144 minus 84 over 3. If you do that calculation, you wind up with 20. Okay, what would the units on that answer be that we just calculated? Well, let's think about the units in our fraction here. So height is measured in feet, t is measured in seconds, so we should be getting units of feet per second. Okay, there's our average velocity between 1 and 4 seconds. Okay, let's remind ourselves too what the graphical meaning of that is. Okay, that represents a slope, and in particular, if we find the two t values, 1 and 4, we just calculated the slope of the line that goes through those 2 points. Okay, I'm going to label that line S1 and just make a remark that that 20 is really the slope of S1. Okay, so then we come to number 2, same idea, just we're talking about a different interval. So the average velocity between 1 and 3, okay, would be the change in height over the change in time, which this time is f of 3 minus f of 1 over 3 minus 1. Okay, and the calculations look very much the same. So we're going to take 3, that's our value of t. To calculate f of 3, we'll plug in 3 for all of our t's. Okay, minus f of 1. We actually already did that calculation above. I'll just go ahead and write it out again though. And then 3 minus 1 is 2. Okay, and if you get numbers for these values, you will discover that that first piece is 156. We already know what this is. Above we got 84. So what we're really wind up with here is 156 minus 84 over 2. And you can double check my calculations there. That ends up being 36. Okay, units are still feet per second, and there's our average velocity between 1 and 3. Okay, how would that look like? What would that look like on our graph? Okay, well, that's the slope of the line between 1 and 3. So here's our point at 1, and our point at 3 is here. And so if we label that line S2, we just calculated the slope of S2. Okay, and you could maybe back off of this for a second and ask yourself, do those answers look reasonable? Okay, so we got a bigger number here for the average velocity between 1 and 3 than we did here between 1 and 4. Does that make sense with the slopes? Notice that it does, because the line S2, that has a steeper slope than S1, so we should get a bigger number for the average velocity between 1 and 3. Okay, so I think we have completed part A here. Let's move on to part B, which is asking us a very interesting question. Okay, or asking us to do something interesting. Use the average velocities in the table below, okay, let's get that into the screen here, to estimate the instantaneous velocity of the object right at t equals 1. Okay, so I'd like to first look at the numbers in the table, see if we can make sense out of those, and then think about how that might help us to answer the question about instantaneous velocity. Okay, so the thing that I want you to notice about the table is that what you're seeing in the second-hand column is a bunch of average velocities. Okay, so for example, in the first row, h is equal to 3. So if you take that value of h and substitute it in here, what you're really going to get is the average velocity on the interval from 1 to 1 plus 3, which would be 4. Notice that that average velocity is what we calculated up here in part number 1. We got an answer of 20, and so our table is confirming the answer that we already got. Okay, and the same is true with h equals 2. If you substitute h equals 2 in here, you're talking about the average value between 1 and 1 plus 2, which would be 3. That 36 is the same number that we got up here. Okay, and the rest of the table is numbers that somebody else calculated for us. So they're just choosing a bunch of other h values and finding the average velocity, doing the same type of calculation as what we did in part A. Okay, now what does this have to do with instantaneous velocity? Okay, that's what they're asking us about. Well, instantaneous velocity is like asking you for the velocity of this object right at the one number t equals 1. Okay, so we're interested in velocities close to t equals 1. Notice that if you go way down to the bottom of the table, that would be the average velocity over a really small time interval, from 1 to 1 plus 0.001. And so because that average velocity takes place over such a short time interval, that means that this last number is probably a pretty good estimate of the velocity right at 1. And if you think about the table as a whole, these average velocities should be approaching the instantaneous velocity. The smaller that h is, the better the approximation is going to be of our instantaneous velocity. Okay, so to answer this question, in part B, ask yourself the following. Does it look like these average velocities are approaching anything? As you go down your table, if you had to guess, what are we getting closer to as h gets smaller and smaller? I would probably pick the number 68. It looks like we're closing in on the number 68. And so that would be our best estimate of the instantaneous velocity based on the data in the table. Okay, we said a lot there, so let's see if we can put that into words. So the average velocities in the table appear to be approaching 68. Okay, and so 68 feet per second is our best estimate of the instantaneous velocity. Okay, so the answer to our question is the 68 that we have here. Okay, now one last thing that I want to add to this discussion here. So we already made the observation that average velocities were slopes of secant lines. We drew in a couple of slopes above. What about the instantaneous velocity? Well, it turns out that that's also the slope of a line. But what we want is the slope of our graph right at just one number t equals 1. And in fact, we can get an idea of what the slope of our function is right at 1 by drawing in this line, the line that just grazes our curve at one point. I'm curious if you might know a name for this type of a line. It's called a tangent line. I'm going to label it t. And its slope should be our instantaneous velocity, that 68 that we guessed. All right, so I'm going to close this discussion here by filling in this blank here. So graphically, the instantaneous velocity of the object at t equals 1 is the slope of the tangent line, t, that we just drew in. Okay, and this tangent line, that's going to occupy a lot of our attention in the days and the weeks to come in our course.